Tonight, we are going to look into the enormous darkness between galaxies. Photographs of the deep universe can make the cosmos appear almost crowded. Thousands of galaxies seem to hang beside one another, their spirals and glowing cores scattered across the same narrow frame. Some look so close that they could almost be touching. But those images have flattened distances that the human mind was never built to understand. Two galaxies that appear side by side may be separated by millions, hundreds of millions, or even billions of light years. Between them lies an expanse with almost no stars, almost no visible light, and sometimes less than a single atom inside a space as large as a room. Even Andromeda, our nearest large galactic neighbour, sits about 2.5 million light-years away. The light entering your eyes when you look toward it tonight began its journey long before modern humans existed. And if we pointed the fastest spacecraft humanity has ever built toward Andromeda, the crossing would take billions of years. Yet even that is only the beginning. Because the distance between galaxies is not simply enormous, much of it is expanding. The galaxies beyond our gravitational neighborhood are being carried farther away as space itself stretches between us. Some remain visible because their ancient light is still arriving, even though no message sent from Earth today could ever reach them. We can see places that have already become permanently inaccessible. And as the universe continues to expand, more galaxies will cross that boundary. The cosmic web will thin. The great clusters beyond our local group will fade from view. In the distant future, the surviving galaxies around us may appear to exist entirely alone, surrounded by a darkness that offers no evidence that the wider universe was ever there. By the end of tonight, you will understand how far apart galaxies truly are, what fills the immense spaces between them, and why the distance separating these islands of stars is becoming worse with every passing moment. Before we begin moving outward, take a moment to settle in and get comfortable. And if these quiet journeys through the universe help you relax, you can support the channel by liking the video and subscribing. It helps these longer explorations reach more people who enjoy learning about space at a slower pace. Now, let us begin with one of the most famous images in astronomy. The Hubble Ultra Deep Field looks like a window cut into a crowded universe. Across a dark background, thousands of galaxies appear in nearly every direction. Some are broad spirals with visible arms. Others are smooth, elliptical shapes, glowing yellow or orange. Many are little more than red points or distorted fragments, their light stretched and weakened by an immense journey through space. The photograph was created by aiming the Hubble Space Telescope toward a small region in the constellation Fornax. The selected patch was deliberately unremarkable. It contained no bright nearby stars and no famous nebulae. To an observer looking from Earth, it would have appeared almost completely empty. Hubble watched that darkness for more than 11 days of combined exposure time. As the telescope gathered light, the emptiness slowly filled. Faint objects emerged from the background until astronomers could identify nearly 10,000 galaxies inside the final image. That number is impressive, but it is also misleading in a very specific way. A photograph records where light appears to come from across the width and height of the sky. It does not naturally show how deeply one object sits behind another. The result is a flat surface containing sources spread across an enormous three-dimensional volume. Imagine looking down a long road at night. A nearby street lamp and a distant light on a hill might appear beside one another from your position. In a photograph, both become points on the same flat image, even though a great distance separates them. The deep field performs the same compression on a far greater scale. One galaxy may lie a few 100 million light-years away. Another beside it may be several billion light-years farther. A third may be so distant that we are seeing it during the universe's early childhood. They share a location in the photograph, but not a common region of space. The image also compresses time. Light from every galaxy began its journey during a different era. The nearer galaxies show us a more recent universe. The distant ones reveal periods when galaxies were smaller, more irregular, and forming stars at much faster rates. Some of the faint red objects appear not as they are now, but as they existed more than 12 billion years ago. A single deep field image, therefore, contains many different chapters of cosmic history layered across the same narrow frame. The galaxies seem to form one crowded population, but they are not all neighbours. Many never existed in the same form at the same time. Some may have merged, changed shape, or stopped producing new stars long before the light of another object in the image had even begun its journey toward Earth. Our minds still place them together. Human vision developed to interpret landscapes where visible objects are separated by meters or kilometers. When two trees overlap in our field of view, our brains estimate which one is closer. When two buildings stand beside each other, we assume they belong to the same general place. That instinct works well on Earth. It becomes unreliable when applied to a photograph containing billions of light-years of hidden depth. This is why the deep universe appears more crowded than it really is. The bright objects remain visible, while the distances between them leave no mark on the flat image. The photograph shows the galaxies, but removes the scale of the emptiness surrounding them. And that emptiness is not a small correction to the picture. It is most of the picture. The visible galaxies occupy comparatively tiny regions where gravity has gathered stars, gas, dust, and dark matter together. Between those concentrated structures lie expanses that can stretch for millions or hundreds of millions of light-years, containing no bright stars and almost nothing that human eyes could detect. To begin understanding those distances, we need something more useful than a photograph. We need a ruler, and the first ruler large enough for the task is the galaxy we already live inside. The Milky Way is easiest to recognize from a dark place, far from city lights. It appears as a pale, uneven band crossing the sky, with brighter patches near the constellations Sagittarius and Scorpius, and dark lanes cutting through its glow. That band is our view from inside a galaxy. The Milky Way has the broad shape of a flattened disk, with a thicker central region and spiral arms curving through it. Earth sits inside one of the smaller features known as the Orion Spur, between the larger Sagittarius and Perseus arms. From this position, we look through long stretches of the disk, where the combined light of distant stars blends into a milky haze. The dark patches are clouds of dust. Individual grains made mainly from carbon-rich material and silicate minerals absorb and scatter visible light, hiding large parts of the galaxy behind them. Infrared telescopes can see through much of this dust, because infrared light passes through the clouds more easily than visible light. The bright stellar disk measures approximately 100,000 light-years from one side to the other. Estimates vary because its outer population fades gradually, and faint stars have been detected beyond the region traditionally treated as the disk's edge. The galaxy's thin gas, scattered outer stars, and enormous dark matter halo extend much farther. Our own location lies roughly 26,000 light-years from the galactic center. This means the light leaving the central region tonight will need about 26,000 years to reach Earth. The light currently arriving from there began its journey when human beings were living during the last ice age. A light year measures distance. It is the distance light travels through a vacuum during 1 year, equal to nearly 6 trillion miles. Light moves at about 186,000 miles every second, making it the fastest signal allowed by modern physics. Across familiar parts of the solar system, that speed seems almost immediate. Light, reflected from the Moon, reaches Earth in about 1¼ seconds. A command sent to a machine on the lunar surface would therefore require a little more than 2½ seconds to travel there and return, even before the machine took any time to respond. Sunlight reaches Earth in a little more than 8 minutes, crossing approximately 93 million miles. When the Sun appears above the horizon, we see its surface as it existed 8 minutes earlier. Light passing across the diameter of Neptune's orbit needs only several hours. Neptune itself lies about 4 light hours from the Sun on average, depending on where Earth and Neptune are located in their paths. A radio message sent from Earth may therefore take around 4 hours to reach the planet, and another 4 hours for a reply to return. Those delays remain short compared with the scale of the Milky Way. A beam of light, beginning at one edge of the bright galactic disk, would travel for roughly 100,000 years before reaching the opposite edge. If the journey began when early modern humans were spreading across parts of Africa and Asia, the beam would only now be approaching the far side. During that crossing, it would pass through a galaxy containing somewhere between 100 billion and 400 billion stars. The uncertainty comes from the difficulty of counting faint red dwarf stars, hidden stars behind dust, and objects in the distant outer disk. Between those stars are enormous clouds of hydrogen, where new stars can form. Some clouds remain cold and dark. Others glow after nearby young stars strip electrons from their atoms. Dust lanes wind through the disk, while the remains of dead stars include white dwarfs, neutron stars, and black holes. Around the galaxy's center, old stars gather into a swollen region called the bulge. Surrounding the disk is a sparse stellar halo containing globular clusters, which are tightly packed groups holding tens of thousands or even millions of ancient stars. The Milky Way also contains magnetic fields stretching across thousands of light years. High-energy particles called cosmic rays move through those fields after being accelerated by exploding stars and other powerful events. At the center lies Sagittarius A, a supermassive black hole with a mass of roughly 4 million suns, packed into a region smaller than the orbit of Mercury around our star. Most of the time it remains comparatively quiet because little nearby material is falling into it. All of these structures belong to one galaxy. Using miles to describe its diameter produces a number with so many digits that it becomes difficult to picture. Light years give the distance a more useful form, while the travel time reveals the real scale. Even light needs 100,000 years to cross the bright disk. The Milky Way can therefore serve as our first intergalactic ruler. Instead of imagining empty gaps as trillions upon trillions of miles, we can ask how many entire galactic disks could fit inside them. The nearest major galaxy begins about 25 Milky Way diameters away. The nearest major galaxy appears in the northern sky as a faint, elongated patch in the constellation Andromeda. Under dark conditions, far from streetlights and moonlight, it can be seen without a telescope. To the unaided eye, it looks modest enough to be mistaken for a thin cloud. That small glow is Messier 31, usually called the Andromeda Galaxy. Andromeda is the nearest major galaxy to the Milky Way. Several dwarf galaxies are much closer. The Large Magellanic Cloud lies about 160,000 light-years away, while the Small Magellanic Cloud is roughly 200,000 light-years from us. These smaller systems contain far fewer stars and orbit within the Milky Way's wider gravitational environment. Andromeda belongs to a different scale. Its central region, spiral disk, satellite galaxies, and surrounding halo form the largest galactic system in our immediate neighborhood. The distance from Earth to Andromeda is approximately 2.5 million light-years. Using the Milky Way's bright disk as a ruler, The gap measures about 25 galactic diameters. An imaginary row of 25 Milky Ways could be placed between the two galactic centers. Even this comparison simplifies the geometry. Andromeda's own stellar disk may extend roughly 200,000 light-years or more, depending on which faint outer stars and structures are included. The galaxy contains hundreds of billions of stars. Broader estimates sometimes place the total near 1 trillion, though counting such a distant population requires models of stars too dim or crowded to observe individually. From Earth, most of that structure remains invisible to ordinary eyesight. The full disk covers an area of sky several times wider than the full moon, but its outer light is spread so thinly that only the brighter central portion is usually noticeable. A telescope reveals more. Long photographic exposures bring out dust lanes wrapped around the center, blue regions containing young stars, and small companion galaxies held nearby by gravity. The Hubble Space Telescope studied Andromeda in extraordinary detail through a project assembled over roughly a decade. More than 600 overlapping observations were joined into a vast mosaic covering a large part of the galaxy's disk. Inside that mosaic, astronomers resolved about 200 million individual stars. Each visible point represented a separate sun or stellar system, yet the image still captured only part of Andromeda's complete population. Many stars remained too faint, obscured, or crowded together to be distinguished. The light recorded in those observations had traveled for about 2.5 million years. When its journey began, Earth was entering the Pleistocene epoch, a long period marked by repeated advances and retreats of large ice sheets. Early members of the human family were living in Africa, but modern humans would not appear for more than 2 million years. During the entire rise of our species, the spread of people across continents, the development of agriculture, and the construction of every city in history, those photons continued moving through the darkness. They arrived carrying an image of Andromeda from the distant past. No telescope has ever shown the galaxy as it exists today. Its present stars, supernovae, gas clouds, and orbiting companions will remain unknown to Earth for another 2.5 million years. Any event happening there tonight has only begun sending its information toward us. Physical travel makes the separation even clearer. NASA's Parker Solar Probe has become the fastest human-made object. During its closest passages near the Sun, the spacecraft has exceeded approximately 430,000 miles per hour. It reaches that speed by falling deep into the Sun's gravity and sweeping through the inner solar system on a carefully designed orbit. At 430,000 miles per hour, Parker could circle Earth in only a few minutes. It could cross the distance from Earth to the Moon in well under an hour. If a spacecraft maintained that record speed all the way to Andromeda, the journey would still last roughly 4 billion years. That estimate ignores the time and fuel needed to accelerate. It also ignores navigation, repairs, collisions with particles, and slowing down near the destination. The simple calculation assumes uninterrupted motion at the highest speed humanity has ever achieved. 4 billion years is close to the current age of Earth. Andromeda earns the description nearby because almost every other major galaxy lies farther away. Its faint patch in the sky marks an entire galactic system separated from us by a crossing comparable to the lifetime of a planet. The apparent gap also assumes that the Milky Way ends at its outermost visible stars and that Andromeda begins at the edge of its bright disk. Both galaxies continue far beyond the light that outlines them. A photograph of Andromeda mainly records the places where stars produce enough light to stand out against the background. Its bright central bulge, curving dust lanes, and broad stellar disk form the familiar visible galaxy. Beyond that light, several more distant layers continue outward. The first is the faint stellar halo. This region contains old stars and globular clusters spread far above and below the main disk. Globular clusters are compact groups that can hold hundreds of thousands of ancient stars. They orbit the galaxy at great distances, often following paths that bear little resemblance to the orderly rotation of stars inside the disk. Farther out, the number of visible stars decreases, but the galaxy's gas continues. Astronomers call this extended reservoir the circumgalactic medium. The name simply means the material surrounding a galaxy. It consists mainly of thin, ionized gas, meaning that energetic radiation has removed electrons from many of its atoms. The circumgalactic medium can contain hydrogen, helium, oxygen, silicon, and other elements produced inside earlier generations of stars. Supernova explosions and powerful stellar winds can push enriched gas outward from a galaxy. Some of that material may later cool and fall back toward the disk, where it can help form new stars. This surrounding gas is extraordinarily difficult to photograph. It produces very little visible light because its particles are separated by large distances. A telescope pointed directly at it may record almost nothing. Astronomers detect the gas by placing a much brighter object behind it. Quasars are useful for this purpose. A quasar is the intensely bright center of a distant galaxy where matter is falling toward a supermassive black hole. Gas circling the black hole becomes hot enough to release enormous amounts of radiation, allowing some quasars to remain visible across billions of light years. When quasar light passes through a galactic halo, atoms and ions in the foreground gas absorb specific wavelengths. A spectrograph separates the arriving light into its component colors, producing a detailed spectrum. Narrow gaps appear, where the intervening material has removed light at particular energies. Each chemical element leaves a recognizable pattern. Hydrogen absorbs one set of wavelengths. Ionized oxygen produces another. The amount and position of this absorption help astronomers estimate the gas's composition, temperature, motion, and density. This method is called absorption line spectroscopy. It allows an almost invisible cloud to reveal itself through the small pieces missing from a brighter source's light. Andromeda's extended halo was mapped through a program known as Project Omega, short for the absorption map of ionized gas in Andromeda. The project used observations from the Hubble Space Telescope to examine the light of approximately 43 quasars positioned behind different parts of Andromeda's surroundings. From Earth, these quasars appear scattered around the galaxy. In reality, they lie far behind it. Their light passed through different regions of Andromeda's halo before reaching Hubble. The measurements revealed a vast structure. Andromeda's circumgalactic medium extends roughly 1.3 million light-years from the galaxy in many directions. Evidence from some lines of sight suggests that parts of it may reach close to 2 million light-years. The visible stellar disk is only a small central feature inside that much larger gaseous environment. A second boundary comes from gravity. Astronomers often use a region called the virial radius to describe the area where a galaxy's gravity strongly controls surrounding matter. The exact boundary depends on how mass and density are defined, so different studies can produce somewhat different values. Beyond the stars and gas lies an even larger concentration of dark matter. Dark matter emits no detectable light, but its gravity affects the motion of stars, gas, and satellite galaxies. The Milky Way and Andromeda each sit inside dark matter halos extending far beyond their bright disks. These halos contain most of each galaxy's mass. The result is a galaxy with no single sharp edge. Starlight fades first. Sparse gas continues much farther. gravitational influence reaches beyond most directly detectable material. The enormous halo around Andromeda may already meet or overlap with the Milky Way's own extended gaseous surroundings. This does not create a dense passage between the galaxies. The material remains extremely thin, with vast distances separating individual particles. The two bright disks still sit millions of light-years apart, but their outer environments are beginning to share the same region of space. That connection places both galaxies inside a larger gravitational family spread across millions of light-years. The Milky Way and Andromeda belong to a larger collection called the Local Group. It contains more than 100 known galaxies spread across a region roughly 10 million light-years wide, although the exact count continues to change as surveys uncover smaller and fainter members. Most of the Local Group's mass is concentrated around two enormous spiral galaxies. One concentration surrounds the Milky Way. The other surrounds Andromeda, which is slightly more massive under many current estimates. A third large galaxy sits nearby by astronomical standards. The Triangulum Galaxy, also known as Messier 33, lies approximately 2.7 million light-years from Earth. Its bright disk measures around 60,000 light-years across and contains tens of billions of stars. Triangulum is smaller than the Milky Way and Andromeda, though it remains far larger than most Local Group members. Its spiral arms contain bright clouds of ionized hydrogen, where new stars are forming. One of these regions, called NGC 604, stretches across more than 1,000 light-years and contains hundreds of young, massive stars. The remaining Local Group galaxies are mostly dwarfs. The Large Magellanic Cloud lies approximately 160,000 light-years from Earth. From the southern hemisphere, it appears as a cloudy patch separated from the main band of the Milky Way. It contains several billion stars and hosts the Tarantula Nebula, one of the most active nearby regions of star formation. The Small Magellanic Cloud lies around 200,000 light-years away. It has been distorted by gravitational interactions with the Large Magellanic Cloud and the Milky Way. A trail of hydrogen gas called the Magellanic Stream extends across a large portion of Earth's sky, recording the long interaction among these galaxies. Other satellites are considerably fainter. The Sagittarius dwarf spheroidal galaxy passes through the outer regions of the Milky Way. It was identified in the 1990s, even though parts of it lie relatively close to Earth, because its stars are spread across the sky and hidden behind dense regions of the galactic disk. Repeated encounters with the Milky Way have pulled long streams of stars away from the dwarf. These streams wrap around our galaxy and allow astronomers to trace Sagittarius's orbit over billions of years. Some Local Group members contain only a few thousand visible stars. These ultra-faint dwarf galaxies can be less luminous than a single large star cluster, while their stellar motions suggest that they contain substantial amounts of dark matter. Deep surveys have revealed many of them during the last several decades. The Dark Energy Survey, which began observations from Chile in 2013, discovered numerous faint satellite candidates around the Milky Way and the Magellanic Clouds. Other wide-field surveys continue searching for systems whose stars blend almost completely into the foreground of our own galaxy. The growing catalogue has no simple outer wall. Local Group galaxies occupy a broad gravitational environment with several possible ways to define its boundary. One useful concept is the zero-velocity surface. Near the center of the Local Group, the combined gravity of its galaxies controls the motion of nearby matter. Farther away, the general expansion of the universe becomes more important. The zero-velocity surface marks the approximate region where outward cosmic expansion and inward gravitational attraction balance. Its exact location depends on the local group's total mass and the motions of surrounding galaxies. Estimates generally place the boundary several million light-years from the group's center. Inside this region, galaxies can approach one another, orbit larger systems, or become disrupted by gravitational encounters. Andromeda is moving toward the Milky Way because both galaxies remain inside the same bound environment. Cosmic expansion becomes clear across much larger distances. It describes how the average separation between unbound regions increases as the universe evolves. Local gravity dominates inside compact systems such as planetary systems, galaxies, and gravitationally bound galaxy groups. This distinction explains why the Milky Way itself is not steadily swelling through expansion. Earth's orbit does not enlarge according to the Hubble flow. The distance between neighboring stars inside the galaxy follows local gravity and motion. The local group behaves in the same general way across a much larger region. Its galaxies remain connected through gravity, even though enormous stretches of thin gas and darkness separate them. That connection remains remarkably sparse. A traveler moving between the Magellanic Clouds, Triangulum, Andromeda, and the many dwarf systems would cross distances lasting hundreds of thousands or millions of light-years. The word group describes a shared gravitational fate, while each bright member remains isolated across a scale far beyond present travel. Today, astronomers can map this family through star counts, motions, redshifts, and the behavior of satellite galaxies. Barely more than a century ago, many astronomers still placed Andromeda inside the Milky Way. At the beginning of the 20th century, astronomers could photograph Andromeda's curved structure, its bright center, and dark lanes crossing its light. Many observers called it the Great Andromeda Nebula, using a word that broadly described a cloudy object whose true nature remained uncertain. Some astronomers believed the spiral nebulae were young planetary systems forming inside the Milky Way. Others argued that each spiral was a separate island universe containing its own stars. The disagreement persisted because apparent size and brightness could not settle the matter. A nearby, relatively small object can look much like a distant, enormous one. Establishing Andromeda's true distance required an object inside it, whose actual brightness could be determined independently. A crucial step came from Henrietta Swan Leavitt. Leavitt worked at the Harvard College Observatory, examining photographic plates of the large and small Magellanic Clouds. These nearby dwarf galaxies offered an important advantage. Their stars were separated from Earth by approximately the same distance compared with the much smaller separations among stars inside each cloud. Among those stars, Leavitt studied Cepheid variables. A Cepheid is a star that repeatedly expands and contracts. As the outer layers move, the star brightens and dims in a regular cycle. Some complete a cycle in only a few days, while others require several weeks. In 1912, Leavitt published a relationship connecting a Cepheid's pulsation period with its luminosity, meaning the total amount of light it produces. Cepheids with longer periods were intrinsically brighter than Cepheids pulsing more quickly. Once astronomers calibrated that relationship, a Cepheid's rhythm could reveal its true brightness. Comparing that true brightness with how faint the star appeared from Earth gave an estimate of its distance. The underlying rule is called the inverse square law. Light spreads outward as it travels. Doubling the distance from a source spreads the same light across 4 times the area, making the source appear 1/4 as bright. Increasing the distance by 3 times spreads the light across 9 times the area. An object whose true luminosity is known can therefore serve as a standard candle. The phrase does not mean that every such object produces exactly the same amount of light. It means that scientists have a reliable method for determining its real output before comparing it with the brightness measured at Earth. Leavitt's Cepheids offered a way to measure distances far beyond ordinary stellar parallax. The uncertainty surrounding the spiral nebulae came into public focus in Washington, D.C. during April of 1920. Harlow Shapley and Heber Curtis presented opposing views at a meeting that later became known as the Great Debate. Shapley had used globular clusters to argue that the Milky Way was much larger than many astronomers had assumed. He correctly placed the solar system far from the galactic center. His model allowed the spiral nebulae to remain inside one enormous Milky Way. Curtis supported a smaller Milky Way and argued that spiral nebulae such as Andromeda were separate galaxies at tremendous distances. He pointed to dark lanes, novae, and the large apparent speeds of some spirals as evidence for the island universe interpretation. Each astronomer held some positions that later proved correct, and others that did not. The debate itself produced no immediate winner because the necessary distance measurement was still missing. That measurement began to emerge several years later from Mount Wilson Observatory in California. Edwin Hubble used the 100-inch Hooker telescope, then the largest operational telescope in the world, to photograph Andromeda. During observations in 1923, he examined a plate containing several objects he initially believed were novae, which are stars that suddenly brighten and later fade. One object behaved differently. Hubble compared the plate with earlier photographs and found that the star had brightened and dimmed repeatedly. He crossed out the letter, marking it as a nova, and wrote var beside it, identifying it as a variable star. The object became known as V1, the first Cepheid variable clearly recognized in Andromeda. By measuring its pulsation period and applying Leavitt's relationship, Hubble estimated the star's true luminosity. Its faint appearance showed that Andromeda had to lie far beyond the accepted limits of the Milky Way. His original distance estimate was much smaller than the modern value of roughly 2.5 million light-years. Problems in the early calibration of Cepheids caused several early extragalactic distances to be underestimated. Even so, Hubble's result placed Andromeda hundreds of thousands of light-years away, much too distant to belong inside the Milky Way. By 1924, the conclusion was becoming clear. Andromeda contained its own population of stars. Its spiral shape belonged to a separate galaxy. Other spiral nebulae were also understood as distant galaxies, rather than small clouds inside our own. The change came from a measurable pattern in pulsating stars, preserved on photographic plates and converted into distance through the behavior of light. Cepheids opened the space between nearby galaxies. Reaching the galaxies much farther away would require additional measuring tools, each extending the scale beyond the one before it. Cepheid variables carried astronomers beyond the Milky Way, though their reach has limits. At greater distances, individual stars become too faint and crowded together for even powerful telescopes to measure reliably. Astronomers solve this problem by building what is called the cosmic distance ladder. Each method works across a particular range. Nearby techniques are used to calibrate methods that reach farther, creating an overlapping chain from the solar neighborhood to galaxies billions of light-years away. The first rung comes from geometry. Hold one finger in front of your face and look at it with your left eye closed. Then, switch eyes. The finger appears to shift against the background because your viewpoint has moved. A nearby star produces the same effect as Earth travels around the Sun. Astronomers observe the star from opposite sides of Earth's orbit, 6 months apart. Those two observing positions are separated by roughly 186 million miles, forming a very long baseline. The star appears to move slightly against much more distant background objects. This tiny apparent shift is called parallax. Once astronomers know the baseline and measure the angle of the shift, simple geometry reveals the star's distance. The European Space Agency's Gaia spacecraft has measured these motions with remarkable precision. Launched in 2013, Gaia repeatedly scanned the sky from a position about 1 million miles from Earth. Its instruments tracked the locations and motions of more than 1 billion stars. For nearby stars, the parallax shift may be measured in thousandths of an arcsecond. An arcsecond is 1/3600th of a degree. At that scale, Gaia is detecting changes far smaller than the apparent width of a human hair viewed from many miles away. Parallax directly calibrates the distances of Cepheid variable stars inside the Milky Way. Once the true distances of those nearby Cepheids are known, their pulsation periods can be connected more accurately with their real luminosities. Cepheids in other galaxies then extend the ladder outward. Astronomers also use an independent stellar marker called the tip of the red giant branch. A low-mass star eventually exhausts the hydrogen in its core and expands into a red giant. Near the end of this phase, the star reaches a predictable maximum brightness before helium fusion begins in its center. In a large population of old stars, astronomers can identify this sharp brightness limit. The apparent brightness of the brightest red giants can then be compared with the expected value to estimate the galaxy's distance. This method works especially well in the quieter outer regions of galaxies, where old stars can be separated more easily from dense dust clouds and young stellar populations. Cepheids and red giants, therefore, provide partly independent ways to test nearby galactic distances. Farther away, astronomers rely on explosions bright enough to outshine entire galaxies. A type Ia supernova usually occurs when a white dwarf star undergoes a runaway thermonuclear explosion. A white dwarf is the dense remnant left after a star similar to the Sun sheds its outer layers. Type Ia supernovae do not all reach exactly the same brightness. Their light curves, the measured rise and decline of brightness over time, contain patterns that allow astronomers to correct for much of the variation. Supernovae that fade more slowly tend to be intrinsically brighter. After this relationship is applied, they become standardized candles capable of measuring distances across billions of light years. At still greater scales, the ladder connects with redshift. Atoms absorb and emit light at precise wavelengths, leaving recognizable lines in a spectrum. When a distant galaxy's lines appear shifted toward longer, redder wavelengths, astronomers measure how much the light has been stretched during its journey. The amount of redshift can be combined with a model of cosmic expansion to estimate distance. This becomes increasingly important when individual stars and even supernovae become difficult to observe. Each rung depends on careful calibration, and small uncertainties can carry upward through the ladder. That is why astronomers compare independent methods and repeatedly improve the measurements. One unresolved difference appears in estimates of the Hubble constant, the number describing how quickly the universe is expanding today. Measurements built from nearby Cepheids and type Ia supernovae often produce values in the low 70s kilometers per second per megaparsec. Estimates inferred from the early universe, especially measurements of the cosmic microwave background, tend to fall in the high 60s. A megaparsec is equal to about 3.26 million light-years. The quoted expansion rate describes how much faster, on average, a galaxy appears to recede for every additional megaparsec of distance. The disagreement is known as the Hubble tension. It may reflect an overlooked measurement effect or some missing feature in the standard cosmological model. Its cause remains unsettled. The difference changes precise calculations while leaving the larger picture intact. Galaxies such as Andromeda are separated from us by distances established through several overlapping forms of evidence. With that distance measured, we can leave the observing platform behind and imagine a position more than 1 million light-years from either galactic disk. At the midpoint between the Milky Way and Andromeda, each galactic center would lie about 1¼ million light-years away. That position would still fall inside a region touched by extremely thin halo material. The outer gaseous envelopes surrounding both galaxies extend far beyond their visible stars, and some measurements suggest that their most diffuse regions may already overlap. Even there, the density would remain so low that the surroundings would feel almost completely empty. The familiar night sky would be gone. From Earth, stars appear scattered across every clear night because we live inside the Milky Way's stellar disk. Many of the points visible without a telescope lie within a few hundred light-years. The dense band crossing the sky comes from looking through thousands of light-years of stars gathered along the galactic plane. Halfway to Andromeda, no nearby stellar population would fill the view. The Milky Way would appear in one direction as a faint, extended patch. Andromeda would form another dim glow on the opposite side of the sky. Their broad shapes might be recorded by sensitive cameras, although their spiral arms would not surround the observer like enormous painted structures. Distance spreads their light across a wide apparent area. Brightness decreases according to the inverse square law. Doubling the distance from a source spreads its light across 4 times as much area. At 10 times the distance, the same light is distributed across 100 times the area. A galaxy contains hundreds of billions of stars, yet those stars do not combine into one concentrated point. Their light is spread across the galaxy's entire visible disk. Astronomers describe this as surface brightness, meaning the amount of light arriving from each small piece of the object's apparent area. At more than 1 million light-years from either galaxy, much of that surface brightness would fall below the sensitivity of human vision. The central regions would remain the easiest portions to detect. The older yellow stars packed near each galactic center would form a muted glow. Dim outer stars and dust lanes would require long camera exposures to reveal. Individual stars would usually disappear into the combined light. A particularly powerful supernova might briefly become visible as a new point. A supernova can release as much light as billions of ordinary stars for a short period. Even such an event would arrive long after it occurred, carrying information delayed by more than 1 million years. The surrounding darkness would supply no nearby source of warmth. A spacecraft could not orient itself by a bright local star. Solar panels would receive almost no useful concentrated energy. The vehicle would need to carry its own long-lasting power source, perhaps relying on nuclear reactions or some technology far beyond anything currently built for spaceflight. Outside the craft, audible sound could not travel. Sound requires particles packed closely enough to pass vibrations from one to the next. Intergalactic gas is far too thin to behave like air. An explosion nearby might release radiation and fast particles, while the surrounding space would remain silent. Scientific instruments would detect more than the eyes. Particle counters would register sparse protons, electrons, and ionized atoms drifting through the region. Ionized means that an atom has lost one or more electrons, leaving it electrically charged. Magnetometers might measure very weak magnetic fields extending through the galactic halos and the material between them. These fields would be far weaker than Earth's magnetic field, though they could still influence charged particles traveling over immense distances. Radiation detectors would record cosmic rays. These are atomic nuclei and other particles moving at high speeds, often accelerated by supernova remnants, active galactic centers, or other energetic environments. Microwave instruments would detect the cosmic microwave background. This radiation fills space in every direction and has a present temperature of approximately 2.725 Kelvin, only a few degrees above absolute zero. It was released when the universe became transparent, about 380,000 years after the Big Bang. Human eyes cannot see microwave radiation, but a suitable receiver would measure its faint signal across the entire sky. Powerful telescopes would also reveal distant galaxies beyond the Milky Way and Andromeda. Their light would appear as small, weak sources scattered across the background. Some would lie tens of millions of light-years away. Others would be observed across billions of years of travel time. The location would therefore contain matter, radiation, and physical fields, despite its nearly featureless appearance. The darkness comes from the low concentration of visible light rather than a complete absence of physical activity. Almost everything present would require instruments to detect, and each measurement would describe material spread across distances too large for ordinary experience. Those hidden particles form the intergalactic medium, a thin environment whose density, temperature, and composition vary dramatically from one region to another. The particles recorded in this region belong to the intergalactic medium, the diffuse material spread through the space outside galaxies and their immediate surroundings. Most of it exists as plasma. Plasma is gas whose atoms have lost some or all of their electrons, leaving a mixture of positively charged nuclei and free electrons. On Earth, plasma appears in lightning, fluorescent lamps, and the glowing outer layers of stars. Between galaxies, it is often so thin that a cubic meter of space may contain only a few particles, or much less. There is no single density that describes the entire intergalactic medium. Inside the filaments connecting clusters of galaxies, the particle count may rise to several particles per cubic meter or more. In the hottest gas-filling rich galaxy clusters, the density can become much higher by intergalactic standards. Deep inside cosmic voids, the average can fall far below 1 particle per cubic meter. A volume comparable to a living room may contain only a small number of atomic nuclei, depending on its position within the larger cosmic web. The material is distributed unevenly because gravity has spent billions of years pulling matter toward denser regions. Gas follows the same broad structure traced by galaxies, collecting along filaments and around clusters, while leaving the interiors of voids increasingly sparse. Hydrogen makes up most of this ordinary matter. Hydrogen is the simplest element, with 1 proton in its nucleus. Helium, which usually contains 2 protons and 2 neutrons, forms the second largest share. Both were produced in enormous amounts during the first few minutes after the Big Bang, long before the first stars formed. Heavier elements such as carbon, oxygen, and iron appeared later inside stars. Supernova explosions and galactic winds pushed some of those elements out of galaxies, mixing them into the surrounding gas. Much of the hydrogen between galaxies has been ionized. Ultraviolet radiation from stars, quasars, and other energetic sources stripped electrons from the atoms. Collisions inside hot gas can produce the same result. Astronomers divide the intergalactic medium into several broad phases according to temperature and ionization. The cooler photoionized phase often has temperatures near 10,000 Kelvin. Photoionized means that energetic light has removed electrons from atoms. This material can be detected in ultraviolet spectra, especially through absorption produced by neutral hydrogen that remains mixed into the gas. Another large component is called the warm-hot intergalactic medium. The name sounds mild, but its temperatures range from roughly 100,000 to 10 million Kelvin. This gas formed as matter fell toward filaments and clusters. The infalling material was compressed and struck by shock waves. A shock wave occurs when gas is forced to slow and compress abruptly, converting organized motion into random particle motion. Those particles can move at hundreds of kilometers per second. A thermometer placed inside such gas would describe an extreme temperature because temperature measures the average kinetic energy of particles. Kinetic energy is the energy an object carries through motion. The effect on a spacecraft would be very different from entering a dense furnace. Heat transfer depends on the energy of each particle and on how many particles strike an object. Earth's atmosphere contains an enormous number of molecules in every cubic meter. Even moderately warm air can transfer energy efficiently because collisions happen constantly. Intergalactic gas may contain only a handful of particles in the same volume. Individual impacts can be energetic, yet long intervals separate them. The total flow of heat remains small. A traveler would still require protection from high-energy particles and radiation. The gas itself would not behave like a hot wind. No pressure would push against a spacesuit, and no surrounding atmosphere would carry warmth evenly across its surface. The most extreme, ordinary gas appears inside massive galaxy clusters. Clusters can contain hundreds or thousands of galaxies bound together by gravity. Between those galaxies lies intra-cluster gas, heated to tens of millions of Kelvin. In some regions, temperatures exceed 100 million Kelvin. At those energies, the gas releases X-rays. Space telescopes such as Chandra and XMM Newton can map the X-ray glow, revealing enormous reservoirs of hot plasma extending across millions of light-years. Cooler intergalactic material often reveals itself in ultraviolet absorption, while radio signals can measure free electrons along even longer paths. Each observing method detects a different part of the same scattered environment. The result is a medium that can be extremely hot, almost invisible, and far thinner than any vacuum naturally found on Earth. For many years, this diffuse gas also appeared to contain less ordinary matter than cosmologists expected. A large fraction seemed to be missing from the nearby universe, and the warm, hot material between galaxies became its leading hiding place. Cosmologists knew approximately how much ordinary matter should exist before they could identify where all of it had gone. Ordinary matter is often described with the word baryonic. A baryon is a particle built from smaller particles called quarks. Protons and neutrons are baryons, so almost every familiar object from hydrogen gas to planets and living tissue belongs to the baryonic part of the universe. The expected amount can be calculated from conditions during the universe's earliest history. During the first few minutes after the Big Bang, the cosmos was hot and dense enough for protons and neutrons to join together. This period is called Big Bang nucleosynthesis. The process produced hydrogen, helium, and small amounts of light elements such as deuterium, which is a heavier form of hydrogen, containing one proton and one neutron. The measured proportions of these elements depend on how many baryons were present. Too much ordinary matter would have produced a different mixture. Too little would also leave a recognizable imbalance. A second measurement comes from the cosmic microwave background, released about 380,000 years later. Small patterns in this radiation record how ordinary matter, dark matter, and light interacted while the early universe was cooling. Both methods point toward a universe in which ordinary matter accounts for only a small share of the total cosmic contents. Dark matter contributes much more mass, while dark energy dominates the overall energy budget. The baryonic portion was still large enough that astronomers expected to find an enormous amount of hydrogen, helium, and heavier elements in the later universe. Much of it was easy to identify. Stars contained a visible portion. Cold hydrogen clouds appeared through radio observations. Hot gas inside galaxy clusters released X-rays. Additional material surrounded galaxies in their extended gaseous halos. When astronomers added these reservoirs together, the total remained too low. Depending on the observing method and the period being studied, roughly 30 to 50% of the expected baryonic matter in the nearby universe was historically difficult to locate. The discrepancy became known as the missing baryon problem. The matter had already existed during the early universe. It could not simply vanish without leaving serious conflicts in well-tested physics. The more likely explanation placed it in a form that ordinary surveys were failing to detect. Computer simulations offered a specific hiding place. As gravity assembled galaxies and clusters, enormous streams of gas fell toward dark matter filaments. The material accelerated, collided, and passed through shock waves. Those shocks converted large-scale motion into random particle motion, heating the gas to temperatures between roughly 100,000 and 10 million Kelvin. This produced the warm, hot, intergalactic medium. Its density was too low to create bright clouds in ordinary photographs. Large portions were also too cool to glow strongly in the X-ray wavelengths used to map the hottest cluster gas. Detection required a bright source positioned far behind the suspected material. In a study published in 2018, a team led by Fabrizio Nicastro examined the quasar 1ES 1553 plus 113. The quasar lies billions of light-years away and produces a strong beam of X-ray radiation as matter falls toward the supermassive black hole at its center. That light crossed several enormous structures before reaching Earth. The European Space Agency's XMM Newton Observatory separated the X-rays into a detailed spectrum. The researchers searched for narrow missing bands created when intervening atoms absorbed photons at specific energies. They found evidence for oxygen-7 in 2 separate regions along the line of sight. Oxygen-7 is oxygen that has lost 6 of its 8 electrons. Removing that many electrons requires an extremely hot environment, making oxygen-7 a useful marker for warm, hot intergalactic gas. The oxygen atoms were rare. Their signal became detectable because the quasar's light crossed an immense depth of material. Tiny amounts of absorption accumulated along the route until they produced measurable features in the spectrum. The results strengthened the case that a substantial share of the missing ordinary matter had been spread through hot, thin filaments between galaxies. It also revealed the limitation of the method. One quasar provides a narrow beam through the universe. Its spectrum describes the matter lying along that particular path, while leaving neighboring regions unmeasured. A larger census required many signals crossing different intergalactic routes, each carrying a record of the free electrons encountered along the way. A different kind of signal allows astronomers to sample many long routes through intergalactic space. Fast radio bursts are brief flashes of radio energy arriving from far beyond the Milky Way. Most last only a few thousandths of a second, yet some release as much energy during that instant as the Sun produces over several days. The first recognized example was reported in 2007 by astronomer Duncan Lorimer and student David Narkovich. They found it while searching archived observations from the Parkes radio telescope in Australia. The original signal had been recorded in 2001 during a survey of the Magellanic Clouds. It appeared as a single, powerful pulse whose frequencies arrived at slightly different times. That timing pattern suggested that the burst had traveled through a great depth of ionized material. Radio waves cover a range of frequencies. Higher frequency waves oscillate more rapidly, while lower frequency waves have longer wavelengths. Both travel at the speed of light through a perfect vacuum. Plasma changes their journey slightly. When a radio pulse passes through free electrons, the lower frequency portion experiences a greater delay than the higher frequency portion. The difference may amount to fractions of a second, but radio telescopes can measure it with high precision. A fast radio burst therefore arrives, stretched across time. The highest frequencies reach the telescope first. Progressively lower frequencies follow in a smooth, curved pattern. Astronomers describe the effect with a quantity called the dispersion measure. It represents the total number of free electrons accumulated along the line of sight from the source to the telescope. A large dispersion measure can result from a long path, a dense region of plasma, or a combination of both. Each burst crosses several distinct environments. The signal begins inside its host galaxy, where gas near the source can add part of the delay. It then travels through the host galaxy's surrounding halo before entering the intergalactic medium. Near the end of the journey, the pulse passes through the Milky Way's halo and stellar disk. Astronomers model these local contributions using maps of galactic electrons and observations of pulsars, which are rapidly rotating neutron stars that also produce precisely timed radio signals. After the Milky Way's share is estimated and removed, much of the remaining dispersion can be assigned to the host galaxy and the material between galaxies. The method becomes especially powerful when astronomers know exactly where the burst originated. Early fast radio bursts were detected by large single-dish telescopes that could identify only a broad region of sky. A burst might disappear before another instrument could locate its host galaxy. Arrays of smaller radio antennas improved the situation. By comparing the arrival time at several separated dishes, astronomers can determine a burst's position with enough accuracy to connect it to a particular galaxy. The Australian Square Kilometre Array Pathfinder, located in Western Australia, became especially important for this work. Its 36 antennas can detect a burst and localize its source during the same observation. Once the host galaxy is identified, optical telescopes measure its redshift. Redshift shows how much the galaxy's light has been stretched during the expansion of the universe and provides an estimate of its cosmological distance. Astronomers can then compare two measurements: the distance to the host and the number of electrons encountered along the route. A nearby burst should generally pass through fewer intergalactic electrons. A more distant burst should accumulate a larger dispersion measure, although the exact value changes because matter is distributed unevenly. This expected relationship became known as the Marquardt relation, after Australian astronomer Jean-Pierre Marquardt. In 2020, Marquardt and his colleagues published an analysis of 5 fast radio bursts that had been accurately localized to distant host galaxies. Their measured dispersion increased with distance in a way consistent with the amount of ordinary matter predicted from the early universe. The result provided an independent census of baryons. X-ray absorption had revealed particular filaments along narrow quasar sightlines. Fast radio bursts measured the total free electron content across separate routes through the cosmos. The initial sample was small, and each burst carried uncertainty from its host galaxy and local surroundings. Later discoveries began expanding the catalogue, allowing astronomers to compare more directions and probe how matter is distributed across the cosmic web. The exact engines producing all fast radio bursts remain under study. Magnetars are the leading source class for at least many of them. A magnetar is a neutron star with an exceptionally strong magnetic field, capable of sudden outbursts that release intense radiation. Whatever creates the pulse, its journey transforms it into a record of the space it crossed. Free electrons, scattered across millions or billions of light years, delay each radio frequency by a slightly different amount. A telescope on Earth receives the completed pattern and uses it to estimate matter that would otherwise remain invisible. Those electrons do not form a uniform fog. They gather along particular routes, thin out inside enormous voids, and follow a framework shaped mainly by matter that produces no light. That hidden framework is traced by dark matter, a form of matter known through its gravity. Under the standard cosmological model, dark matter accounts for about 85% of all matter in the universe. Ordinary matter, the atoms inside stars, planets, gas clouds, and living organisms, provides the remaining 15%. Dark matter has not been seen producing, reflecting, or absorbing light. Astronomers infer its presence by measuring how visible objects move and how light travels through regions containing more gravity than the visible material can explain. Some of the earliest evidence appeared inside galaxy clusters. During the 1930s, Swiss astronomer Fritz Zwicky studied the Coma cluster, a rich collection of galaxies roughly 300 million light-years from Earth. He measured how quickly individual galaxies were moving through the cluster. The observed speeds were surprisingly high. A cluster held together only by the stars and visible gas should have allowed many of those galaxies to escape. Zwicky calculated that the system required far more mass to remain bound. He used the German phrase dunkle Materie, meaning dark matter, for the unseen material providing the additional gravity. Later observations found the same general problem within individual galaxies. Stars orbit a galactic center in the same broad way that planets orbit a star. The orbital speed depends on how much mass lies inside the star's path. If most of a galaxy's mass were concentrated in its bright central region, stars farther from the center should move more slowly. During the 1970s, astronomers Vera Rubin and Kent Ford measured the rotation of spiral galaxies with greater precision. They used spectrographs to observe glowing hydrogen clouds and stars on opposite sides of each galactic disk. One side moved toward Earth, shifting its light toward shorter wavelengths. The other side moved away, shifting its light toward longer wavelengths. These changes allowed Rubin and Ford to calculate orbital speeds across the galaxy. The outer regions remained unexpectedly fast. Stars far beyond the bright central bulge often traveled at nearly the same speed as stars much closer to the center. The pattern became known as a flat rotation curve. Visible stars and gas could not supply enough gravity to maintain those orbits. The measurements indicated that each galaxy was embedded inside a much larger halo of unseen mass, extending far beyond its luminous disk. Dark matter halos now form a central part of modern galaxy models. The Milky Way's dark matter halo may extend hundreds of thousands of light-years from the galactic center. Its exact mass and boundary remain uncertain because the material cannot be photographed directly. Astronomers estimate both by tracking satellite galaxies, globular clusters, stellar streams, and fast-moving stars in the outer galaxy. Galaxy clusters reveal even greater quantities. A massive cluster can contain hundreds or thousands of galaxies surrounded by gas heated to tens of millions of Kelvin. This intracluster gas often contains more ordinary matter than all the cluster's stars combined. Even after astronomers include that hot plasma, the cluster still requires several times more mass to explain its motions. Gravity also changes the path of light. According to general relativity, mass curves the surrounding structure of space and time. Light passing near a massive object follows that curvature, causing distant galaxies to appear stretched, duplicated, or magnified. This effect is called gravitational lensing. Strong lensing can produce long luminous arcs around a galaxy cluster. Weak lensing creates smaller distortions in the shapes of many background galaxies. By averaging those subtle distortions, astronomers can construct a map of the total mass lying in front of them. The map includes luminous stars, hot gas, and any unseen material contributing gravity. A particularly useful example is the Bullet Cluster, located several billion light-years away. It formed when two galaxy clusters passed through each other. The hot gas in the clusters collided, slowed down, and remained near the central collision region. Individual galaxies passed through more freely because the distances between stars are enormous. Gravitational lensing maps showed that most of the cluster mass traveled with the galaxies rather than remaining with the colliding gas. The separation provides strong evidence for a large component of matter that interacts weakly with ordinary gas while continuing to exert gravity. No experiment has yet confirmed the identity of a dark matter particle. Detectors beneath mountains have searched for rare impacts. Particle accelerators have looked for invisible products, carrying away energy. Astronomical observations continue testing whether dark matter behaves as expected across galaxies and clusters. Its gravitational effects remain clear even while its microscopic nature stays unknown. Dark matter halos surround galaxies, and larger concentrations connect through filaments extending across millions of light years. Ordinary gas falls into these gravitational structures, where it can cool, form stars, and eventually become visible. The galaxies in deep field photographs, therefore, mark the brightest locations inside a much larger invisible network. That network describes where matter has gathered today. Its origin lies in tiny variations preserved within the much smoother radiation left from the early universe. The earliest map of this structure comes from radiation released when the universe was about 380,000 years old. Before that time, space was filled with a hot, opaque plasma. Free electrons scattered light constantly, much as water droplets scatter the beam of a car headlight inside thick fog. As the universe expanded, its temperature fell. Electrons joined with atomic nuclei to form neutral atoms, allowing light to travel freely across space. That ancient light is now called the cosmic microwave background. Expansion has stretched it into microwave wavelengths and cooled it to about 2.725 Kelvin. Across most of the sky, the background has almost the same temperature. The differences are only about 1 part in 100,000. A patch measuring slightly warmer or cooler than average represents a tiny variation in the density and motion of matter during the early universe. These faint patterns became visible through a series of increasingly precise space missions. NASA's Cosmic Background Explorer, usually called COBE, launched in 1989. In 1992, its science team announced the first clear detection of large-scale temperature variations in the microwave background. The Wilkinson Microwave Anisotropy Probe followed in 2001. It mapped the full sky with much finer detail from a stable location roughly 1 million miles from Earth. The European Space Agency's Planck Observatory launched in 2009 and produced the most detailed full-sky maps of the background yet made. Its measurements allowed scientists to estimate the universe's age, composition, expansion history, and early density pattern with remarkable precision. The map appears mottled, though the physical differences were extremely small. Some regions contained slightly more matter than average. Others contained slightly less. Gravity amplified those differences. A region with a small excess of matter exerted a little more gravitational attraction on its surroundings. Nearby material began moving toward it, increasing the region's mass and strengthening its pull. This process is called gravitational instability. The growth happened slowly at first. Over millions and then billions of years, the original variations became much larger. Dark matter played an important early role because it did not interact strongly with light. Ordinary matter consisted largely of charged protons, electrons, and atomic nuclei. Before the cosmic microwave background was released, those particles were closely linked with radiation. Photons pushed against the plasma, making it difficult for ordinary matter to collapse into compact structures. Dark matter responded mainly to gravity. It could begin gathering into denser concentrations, while ordinary gas remained influenced by radiation. After neutral atoms formed and light began traveling freely, ordinary matter was able to fall into the gravitational wells already created by dark matter. A gravitational well is a region where concentrated mass makes it harder for surrounding material to escape. Gas flowed toward these wells and became compressed. Compression raised its temperature. In sufficiently dense regions, the gas later cooled by releasing radiation, allowing it to contract further. The first stars formed inside small dark matter halos a few 100 million years after the Big Bang. Groups of early stars collected into young galaxies. Smaller halos merged into larger ones, carrying their stars and gas with them. This gradual construction is known as hierarchical structure formation. Small systems formed early and combined over time to produce larger galaxies, galaxy groups, and massive clusters. The process did not gather matter into isolated spheres. Gravity pulled material along several directions at once. Broad regions collapsed into sheets. Matter within those sheets flowed toward narrower filaments. The densest intersections became nodes where galaxy clusters could form. Simulations show this pattern as a web stretching across hundreds of millions of light years. Dark matter supplies most of its mass, while galaxies and hot gas make portions of it observable. The underdense regions changed at the same time. Matter near the edge of a slightly empty region felt a stronger pull from denser structures outside it. Over time, material flowed away from the interior and towards surrounding walls and filaments. As the universe expanded, these low-density regions grew more quickly than dense structures held together by gravity. Their interiors became increasingly sparse, producing the cosmic voids found between major filaments. Galaxies and voids therefore share the same origin. The motion that concentrated matter into luminous structures also removed matter from the spaces around them. By the present era, the tiny variations recorded by Planck have grown into dark matter halos surrounding galaxies, filaments extending across vast distances, and clusters containing thousands of galactic systems. No observer can travel outside this structure and photograph it as a complete object. Astronomers reconstruct its shape from inside, using the positions, redshifts, and motions of millions of galaxies spread across the sky. Astronomers build three-dimensional maps of the cosmic web by measuring where galaxies appear in the sky and how strongly their light has been redshifted. One of the best-known projects is the Sloan Digital Sky Survey, which began regular observations in 2000 from Apache Point Observatory in New Mexico. Its telescope repeatedly photographed large areas of the northern sky and collected spectra from millions of galaxies, quasars, and stars. A spectrum separates light into its component wavelengths. Familiar chemical elements leave narrow lines at known positions. When those lines appear shifted toward longer wavelengths, astronomers can calculate the object's redshift. For galaxies far beyond the local group, a larger redshift usually indicates a greater distance. Combining that estimate with the galaxy's direction places it inside an approximate three-dimensional map. Early redshift maps produced a striking pattern. Galaxies did not fill space evenly. They gathered into curved walls and narrow filaments, while broad, empty regions opened between them. When the data were displayed as slices, the structure sometimes resembled foam, with galaxies concentrated around the edges of enormous bubbles. Redshift alone does not provide a perfect position. A galaxy's observed motion contains the general expansion of the universe and an additional local component created by nearby gravity. That local deviation is called peculiar velocity. The name refers to motion peculiar to the galaxy's surroundings. A galaxy may be carried outward by cosmic expansion while also falling toward a nearby cluster. Its measured redshift contains both effects. Astronomers estimate peculiar velocity by comparing the distance expected from cosmic expansion with a separate distance measurement. The difference shows whether the galaxy is moving slightly toward or away from us relative to the average expansion pattern. Groups of these motions reveal where gravity is pulling matter. In 2014, R. Brent Tully and an international team used thousands of galaxy velocities to map a broad basin of gravitational flow containing the Milky Way. They named the region Laniakea, a Hawaiian word often translated as immense heaven. Laniakea spans approximately 500 million light-years and is commonly associated with around 100,000 galaxies. The Milky Way occupies a small outer branch within this much larger arrangement. The mapped flows converge toward a region known as the Great Attractor. The Great Attractor is not a single hidden object. It describes a concentration of mass influencing the motions of many nearby galaxies. One important structure in that direction is the Norma cluster, also called Abell 3627, located roughly 200 million light-years away. Observing the region is difficult because it lies behind the crowded center of the Milky Way. Dust and foreground stars obscure much of the visible light, creating an area historically called the zone of avoidance. Radio and X-ray observations can penetrate or bypass some of that obstruction. These measurements reveal hot gas, galaxies, and additional mass concentrations hidden behind the galactic plane. Laniakea is useful as a map of galactic flow, though its boundary does not describe one permanently bound object. Some parts remain too widely separated for their mutual gravity to overcome cosmic expansion forever. The name therefore marks a basin of motion in the present universe. Matter inside different portions generally flows toward related dense regions, even though the full supercluster may separate over extremely long periods. Modern surveys add another layer by mapping mass that produces little or no light. The European Space Agency launched the Euclid Space Telescope in 2023. Euclid was designed to survey roughly 15,000 square degrees, covering more than 1/3 of the sky beyond the crowded plane of the Milky Way. Its observations include more than 1 billion distant galaxies, extending across much of cosmic history. Euclid studies galaxy clustering, which measures how galaxies gather at different distances and times. It also records weak gravitational lensing. Weak lensing occurs when foreground matter slightly distorts the shapes of more distant galaxies. The change in any single image is extremely small. By measuring millions of background galaxies, astronomers can detect a shared pattern of stretching and reconstruct the unseen mass responsible for it. These maps trace dark matter across broad regions and show how its distribution changed as the universe evolved. The Vera C. Rubin Observatory in Chile adds a complementary view. Its wide-field telescope was designed to photograph much of the southern sky repeatedly, recording changes over time while building a deep catalogue of billions of objects. Repeated imaging can reveal supernovae, moving objects, and variable sources, while also improving measurements of galaxy shapes and large-scale structure. No single survey provides a complete cosmic map. Redshifts estimate depth, peculiar velocities reveal local gravitational flow, and weak lensing traces total mass. Together, these methods place the Milky Way on a thin branch of a much larger network. The bright clusters and filaments attract attention because they contain galaxies. The maps also show that these crowded structures occupy only a small share of the total volume surrounding them. The broad spaces between filaments are called cosmic voids. They contain galaxies, gas, and dark matter, though each is present at a much lower density than the cosmic average. A typical void may extend across tens of millions of light-years. The largest examples reach several hundred million light-years from one side to the other. Under many mapping systems, these underdense regions occupy most of the universe's total volume. Their shape is rarely a perfect sphere. Voids press against neighboring walls and filaments, producing broad cavities with irregular boundaries. Several smaller voids may also connect into a larger, underdense region. The structure develops through the same gravitational process that builds clusters. A slightly dense region pulls matter toward itself. Gas and dark matter move toward nearby filaments, while the underdense interior loses material. As the universe expands, the sparse region grows more freely because it contains less gravity to slow its expansion. This creates a difference in growth. Dense regions collect matter and become increasingly crowded. Voids lose matter and become increasingly empty. The process unfolds over billions of years. A galaxy near the edge of a void may drift toward the surrounding wall. Dark matter also moves outward from the interior, leaving the remaining particles spread across a larger volume. The center becomes thinner, even though it never reaches perfect emptiness. One of the best-known examples lies in the direction of the constellation Boötes. In 1981, astronomers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Scheckman published results from a redshift survey designed to map galaxies across a particular part of the sky. The survey revealed a surprisingly large region, containing very few known galaxies. This became known as the Boötes void. Modern estimates commonly place its diameter near 330 million light-years, though its exact boundary depends on how astronomers define the surrounding galaxy distribution. That distance is more than 3,000 times the width of the Milky Way's bright disk. If the Milky Way were placed near the center of such a region, the nearest large concentrations of galaxies could lie hundreds of millions of light-years away. A deep survey would still detect scattered systems inside the void, but their separation would be far greater than the spacing found inside a rich cluster. The Boötes void does contain galaxies. Some were discovered after the original survey reached deeper limits. The void's name describes a severe shortage rather than total absence. Galaxies found inside voids are often relatively small and isolated. Many contain abundant cold gas, which can support continuing star formation. They experience fewer major mergers because large neighbors are uncommon. Even these isolated galaxies tend to form along faint internal filaments. The cosmic web continues inside voids at a much weaker level, producing delicate strands that connect sparse groups. A void, therefore, has structure within its emptiness. The Milky Way also sits near an underdense region called the local void. It begins beside the local group and extends through a broad area with relatively few known galaxies. Our own motion reflects this nearby geography. The local group moves through space under the influence of several mass concentrations. Part of that motion also appears connected to the lack of matter inside the local void. Dense regions pull nearby galaxies toward them, while an underdense region produces an apparent movement away because there is less gravitational attraction on that side. Measurements of nearby galaxy velocities help astronomers separate these effects. A still larger proposed feature is often called the KBC underdensity, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie. Studies of galaxy brightness and number density have suggested that the Milky Way may reside inside a region containing less matter than the cosmic average across a scale approaching 1 or 2 billion light-years. The size, depth, and interpretation of this feature remain debated. Different surveys use different galaxy populations, distance ranges, and methods for correcting observational bias. Some analyses find evidence for a meaningful local underdensity, while others conclude that the contrast is smaller or compatible with ordinary large-scale variation. The proposal remains useful because it shows how difficult cosmic cartography becomes at the largest scales. Dust, incomplete sky coverage, uncertain distances, and the selection of visible galaxies can all change the apparent boundary of a structure. Voids themselves remain an established part of the cosmic web. Their combined volume greatly exceeds the narrow regions occupied by rich clusters and luminous walls. Most galaxies live along the denser boundaries, appearing like lights gathered around the edges of immense dark chambers. Position within that structure affects more than the distance to a neighbor. It changes how often galaxies collide, how easily they retain gas, and how long they continue forming new stars. Galaxies inside voids develop under very different conditions, from galaxies packed into rich clusters. A cluster may contain hundreds or thousands of galaxies moving through the same gravitational environment. Between them lies the intracluster medium, a reservoir of extremely hot plasma that can reach temperatures of tens of millions of Kelvin. This gas is thin by earthly standards, yet a galaxy can encounter enough of it over millions of years to lose part of its own colder material. The process is called ram pressure stripping. In 1972, astronomers James Gunn and Richard Gott described how a galaxy moving through cluster gas experiences pressure across its leading side. The effect resembles air pushing against rain while a car moves forward, though the densities involved are vastly lower and the distances are measured in hundreds of thousands of light-years. A spiral galaxy carries large clouds of cold hydrogen inside its disk. This gas provides the raw material for future stars. As the galaxy travels through the intracluster medium at speeds that can exceed 1,000 kilometers per second, pressure pushes against those clouds. Gas held loosely in the outer disk can be swept backward. Denser gas near the center often remains attached longer because the galaxy's gravity holds it more strongly. Some of the clearest examples are known as jellyfish galaxies. Their stellar disks remain visible near the front, while long tails of stripped gas extend behind them. The tails may contain glowing knots where compressed material briefly forms new stars before dispersing into the cluster. ESO 137-001, located in the Norma cluster, roughly 200 million light-years away, displays several bright gas tails stretching more than 200,000 light-years. Chandra X-ray observations revealed hot material flowing behind the galaxy, while Hubble images showed young stars forming inside parts of the stripped gas. The appearance records a galaxy being separated from its fuel supply. Star formation begins inside cold, dense clouds, especially molecular clouds, containing hydrogen molecules. Gravity pulls sections of these clouds inward until pressure and temperature become high enough for nuclear fusion to begin inside new stars. When a galaxy loses cold gas, that process gradually weakens. Existing blue stars continue shining for a while, but the most massive ones survive only a few million years. After they die, the galaxy becomes increasingly dominated by older, cooler stars with yellow and red light. Astronomers call this environmental quenching. Quenching means that star formation has slowed greatly or stopped because the necessary gas has been removed, heated, or prevented from cooling. Dense environments affect galaxies through gravity as well. A close passage can stretch stars into long tidal tails. Repeated fast encounters inside a cluster can disturb a galaxy's disk through a process called galaxy harassment. Each encounter may be brief, but many encounters over billions of years can thicken the disk, scatter stars into wider orbits, and reduce the orderly spiral structure. The relationship between galaxy shape and environment was recognized during the 20th century. Elliptical and lenticular galaxies are common in dense cluster centers, while spiral galaxies appear more frequently in less crowded regions. This pattern is known as the morphology-density relationship. Morphology means physical form. A spiral galaxy usually contains a rotating disk with gas, dust, and ongoing star formation. An elliptical galaxy has a smoother shape and often contains an older stellar population with less cold gas. Mergers can also transform galaxies. A major merger occurs when two galaxies of roughly similar mass combine. Their stars rarely collide directly because the spaces between stars are enormous. Their gravitational fields still disrupt both systems, while gas clouds collide, compress, and sometimes produce intense bursts of star formation. A minor merger involves a much smaller galaxy being absorbed by a larger one. These events can add stars to the outer halo, disturb the disk, and deliver gas toward the central region. Gas driven inward may feed a supermassive black hole. Material circling the black hole heats before crossing the event horizon, creating an active galactic nucleus capable of releasing enormous amounts of radiation. Void galaxies usually avoid the most violent cluster processes. Many retain larger supplies of neutral hydrogen and continue forming stars. Their colors are often relatively blue because young, massive stars contribute strongly to their light. They also tend to be smaller and less massive than the largest cluster galaxies. The pattern has exceptions. Some void galaxies have already exhausted much of their gas, and some cluster galaxies continue forming stars. A galaxy's history depends on its mass, orbit, merger record, and access to fresh material. Environment changes the probabilities. A galaxy surrounded by hot plasma and frequent encounters faces repeated pressure on its gas and structure. A galaxy inside a sparse void may evolve more quietly for billions of years, with fewer large neighbors passing close enough to disturb it. Distance, therefore, shapes more than isolation. It helps determine how much gas a galaxy keeps, how often its stars are rearranged, and how long its spiral arms remain active. The image reaching Earth reveals those changes only after light has crossed the space between us. Every additional light year also adds another year of delay. The light arriving from a galaxy carries an image from an earlier stage of its life. Andromeda appears as it was about 2.5 million years ago. Any supernova occurring there today, any new star cluster forming inside one of its spiral arms, and any change in the motion of its central black hole will remain unseen from Earth until that light completes the crossing. Farther away, the delay becomes much larger. The Virgo cluster lies roughly 54 million light-years from Earth. It contains well over 1,000 known galaxies and forms the nearest major galaxy cluster to the local group. The light reaching us from Virgo began its journey during the Eocene epoch. At that time, Earth's climate was much warmer than today. Early whales were beginning to evolve from land-dwelling ancestors, and the first primates had already appeared. A telescope aimed at Virgo, therefore, observes a collection of galaxies from tens of millions of years in the past. Their current positions, star-forming regions, and interactions are hidden behind the remaining travel time. Distant quasars deepen the delay into billions of years. Some quasars are observed as they existed when the universe was less than 1 billion years old. Their central black holes were already feeding rapidly, drawing surrounding gas into hot disks that released more light than entire ordinary galaxies. The most distant galaxies found by the James Webb Space Telescope are seen during the universe's first few 100 million years. Their stars formed before the Milky Way developed its present spiral structure and before the Sun existed. Astronomers call this delay look-back time. Look-back time describes how long the observed light has been traveling. Andromeda has a look-back time of about 2.5 million years. A galaxy observed 10 billion years into the past has a look-back time of roughly 10 billion years. This sounds as though the galaxy should simply be 10 billion light-years away. Cosmic expansion makes the relationship more complicated. While the light travels, the space between the source and Earth continues changing. The galaxy may be much farther away now than the distance suggested by the photon's travel time. Astronomers therefore use several definitions of distance, each suited to a different measurement. Proper distance describes the separation between two locations at a particular moment in cosmic time. It is the kind of distance that would be measured by an imaginary chain of rulers laid across space at that instant. Co-moving distance removes the effect of expansion from the coordinate system. Galaxies carried apart by the general expansion retain fixed co-moving positions unless they also have significant local motion. This allows astronomers to describe where a distant galaxy would lie within the universe's present large-scale map. Luminosity distance is connected to brightness. It tells astronomers how distant a source appears based on how faint its light has become after spreading outward and being affected by cosmic expansion. These distances can produce different numbers for the same galaxy without contradicting one another. Each number answers a different physical problem. Redshift helps connect them. As light crosses expanding space, its wavelength grows. A photon emitted as visible light may arrive shifted toward the red or infrared part of the spectrum. Astronomers measure this cosmological redshift by comparing known atomic lines with their observed positions. A larger shift generally indicates that the light has crossed a universe that expanded by a greater amount during its journey. The effect explains a fact that can initially seem impossible. The universe is about 13.8 billion years old, yet the present radius of the observable universe is roughly 46.5 billion light-years. The oldest light has traveled for less than 13.8 billion years because the universe was not transparent at the beginning. During that journey, expansion increased the distance between Earth and the regions that emitted the light. Those regions are now much farther away than 13.8 billion light-years when described in present co-moving distance. A deep field image therefore serves as more than a map of remote objects. Its nearby galaxies belong to relatively recent cosmic history. More distant systems show periods when galaxies were smaller and more irregular. The faintest sources record the early stages of galaxy formation. Looking farther across space changes the era being observed. No telescope presents the distant universe as it exists everywhere at one shared moment. Each object appears according to the time required for its light to reach us. The delay continues changing because the distance itself evolves throughout the journey. That changing separation appears in the redshift of distant galaxies. During the 1920s, astronomers compared galactic distances with the wavelengths recorded in their spectra. Georges Lemaitre showed that an expanding universe should produce a relationship between distance and recession. Edwin Hubble later published observations demonstrating that more distant galaxies generally had larger redshifts. The relationship is now called the Hubble-Lemaitre law. Its expansion rate is usually expressed in kilometers per second per megaparsec. 1 megaparsec equals about 3.26 million light-years. A value near 70 kilometers per second per megaparsec means that, on average, each additional megaparsec of distance adds roughly 70 kilometers per second to a galaxy's recession rate. A galaxy located 100 megaparsecs away would therefore follow the general expansion at several thousand kilometers per second, although its exact measured motion would also include local gravitational effects. Those local deviations are called peculiar velocities. The Andromeda galaxy provides a familiar example. It is moving toward the Milky Way, even though the universe expands on larger scales. Both galaxies remain inside the gravitationally bound local group, where nearby gravity controls their relative motion. The same protection applies at smaller scales. Earth remains in orbit because the Sun's gravity holds the solar system together. Stars remain bound inside the Milky Way, and the galaxy's disk does not expand according to the Hubble-Lemaitre law. Expansion becomes dominant across the great distances separating unbound galaxy groups and clusters. A useful way to describe the process comes from geometry. Imagine many points marked on a flexible surface. As the surface stretches, the distance between widely separated points grows. Each point sees distant points receding, even though the surface has no special central mark from which everything was launched. The real universe has 3 spatial dimensions, so every simple surface analogy eventually reaches its limits. The central idea remains useful. The large-scale rule used to measure separation changes as cosmic time passes. Light traveling between 2 remote galaxies therefore crosses a changing distance. The source continues receding while the photon moves, and the photon's wavelength stretches along with the expanding space. For much of cosmic history, gravity slowed the expansion. Matter attracts matter. When the universe was younger and denser, the combined gravity of dark matter and ordinary matter acted strongly against the outward expansion. Cosmologists expected this slowing to continue, though perhaps never strongly enough to reverse the universe into a collapse. Observations during the late 1990s produced a different result. 2 research groups were studying type Ia supernovae in distant galaxies. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Z Supernova Search Team, whose leading researchers included Brian Schmidt and Adam Rees. Type Ia supernovae can be standardized by measuring how their brightness rises and fades. Once their true luminosity is estimated, their apparent faintness provides a distance. The teams compared those distances with the supernovae's redshifts. Their results, announced in 1998, showed that many distant supernovae appeared dimmer than expected in a universe whose expansion was simply slowing. The observed pattern indicated that cosmic expansion had entered an accelerating phase. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. The name dark energy was adopted for the unknown component driving the acceleration. Under the standard cosmological model, dark energy accounts for roughly 2/3 of the universe's total energy density. The simplest working description uses the cosmological constant, commonly represented by the Greek letter lambda. Albert Einstein originally introduced a cosmological constant into his equations of general relativity in 1917. In modern cosmology, lambda represents a constant energy associated with empty space. As the universe expands and creates more volume, this energy density remains approximately unchanged. Matter becomes more diluted as space grows. Dark energy therefore becomes increasingly important compared with matter as cosmic time passes. Measurements from supernovae, the cosmic microwave background, and large-scale galaxy surveys support this broad picture. The underlying physical nature of dark energy remains unknown. Scientists continue testing whether its strength has stayed constant or changed during cosmic history. Under the simplest model, accelerated expansion continues indefinitely. Unbound galaxy groups become increasingly separated. Ancient light may still reach us from a remote system, while its present position recedes much farther than the image suggests. The gulf has gained a new property. It grows during the attempted crossing. Some photons can still overcome that growth and arrive. Others begin beyond distances where future expansion prevents any signal sent today from completing the journey. The dividing line depends on several different cosmic horizons, each describing a different limit on what can be observed or reached. Several different boundaries surround our observable region, and each describes a different limit. The largest familiar one is the observable universe. It contains every region from which light has had enough time to reach us since the early universe became transparent. Measured in present-day co-moving distance, its radius is roughly 46.5 billion light-years. Its full diameter is therefore close to 93 billion light-years. That size exceeds the universe's age of about 13.8 billion years, because the regions that released the oldest light continued moving farther away while the light traveled toward us. Co-moving distance describes where those regions fit within the universe's present large-scale map. A different boundary is called the Hubble sphere. At the Hubble sphere, the recession rate predicted by the current expansion law equals the speed of light. Its present radius is roughly 14 billion light-years, depending on the chosen expansion rate. Galaxies beyond this distance can recede from us faster than light. This does not violate special relativity. The speed limit applies to objects moving locally through space. Cosmological recession comes from the changing distance created by expanding space across an enormous region. The Hubble sphere also does not form a solid wall. Light emitted beyond it can sometimes reach Earth because the Hubble sphere changes over time. A photon may begin in a region receding faster than light, make little progress at first, and later enter a region where the expansion conditions allow its distance from us to decrease. Some galaxies we observe today were already beyond the Hubble sphere when they released the light now arriving. A broader boundary is the particle horizon. The particle horizon marks the greatest present comoving distance from which any information could have reached us since the beginning of cosmic history. It closely corresponds to the outer limit of the observable universe. Everything beyond it remains unseen because insufficient time has passed for a signal to complete the journey. The most important boundary for future travel is the cosmic event horizon. The event horizon depends on the entire future behavior of expansion. It separates regions that can still exchange newly emitted signals from regions that can never communicate with us, assuming the current cosmological model continues. Its present scale is often placed near 16 billion light-years in comoving distance, though the exact number depends on the cosmological parameters and the definition used. A galaxy can therefore occupy a strange category. Its ancient light may remain visible in our telescopes. The galaxy may appear in a deep survey with a measurable redshift and a recognizable shape. A signal transmitted from Earth today could still fail to reach its present region, even if the signal traveled at light speed forever. The photons we receive began their journeys when the galaxy was closer and the universe was smaller. They crossed the intervening distance before accelerated expansion created the conditions that now prevent a new signal from following the same general route. Visibility records a successful journey from the past. Reachability concerns a journey beginning now. Under the standard model, dark energy behaves like a constant energy of empty space. Expansion continues, accelerating, and sufficiently distant regions gain separation faster than future light can overcome. This leads to a widely repeated estimate that only around 6% of the galaxies currently inside the observable universe remain reachable by an idealized signal sent from Earth today. The corresponding statement says that roughly 94% are already unreachable. Those percentages are model-dependent. They rely on assumptions about the expansion rate, the amount of matter and dark energy continuing to behave like a cosmological constant. They also depend on how galaxies are counted across cosmic history. The precise fraction may change as measurements improve. The larger consequence remains. Most of the galaxies represented in the observable universe cannot become destinations, even for an imagined traveler moving at the maximum speed allowed by physics. Their light can enter our instruments, while our own future light can never enter their present surroundings. A distant galaxy may remain visible for billions of years as its arriving photons become fainter and more redshifted. Each image acts as an increasingly ancient record of a place that has moved outside our possible future. The universe therefore contains regions that belong to our observational past, while remaining absent from every possible exchange beginning now. Expansion creates that separation for most galaxies. Andromeda provides a more generous test. It remains gravitationally bound within the local group, so cosmic acceleration will not carry it beyond our reach. Any failure to cross that nearer gulf must come from the limits of speed, energy, engineering, and survival. Andromeda remains inside the local group's gravitational boundary, so cosmic expansion does not remove it from our possible future. A spacecraft aimed in that direction would still face a journey of approximately 2.5 million light-years. At the record speed reached by Parker Solar Probe, the crossing would last roughly 4 billion years. That comparison gives present technology almost no practical role, so the calculation must move into speeds that no spacecraft has approached. At 10% of light speed, a vehicle would travel nearly 18,600 miles every second. The journey to Andromeda would still require about 25 million years as measured from Earth. 25 million years ago, the planet was in the Oligocene epoch. Grasslands were spreading across several continents, and the earliest apes were beginning to appear. A ship leaving during that period would only now be reaching its destination. Increasing the speed to 90% of light changes the calculation dramatically, while leaving an immense duration. Observers on Earth would measure a journey of roughly 2.8 million years. Relativity would shorten the time experienced aboard the ship, because clocks moving at extreme speed pass more slowly when compared with clocks left behind. The size of this effect is described by the Lorentz factor. At 90% of light speed, the Lorentz factor is approximately 2.29. Dividing the Earth frame journey by this amount gives an onboard duration near 1.2 million years, ignoring acceleration and deceleration. No human society has survived for anything approaching that span. Homo sapiens has existed for only around 300,000 years. At 99% of light speed, the Lorentz factor rises to approximately 7.09. Earth would still record a little more than 2.5 million years, while travelers would experience roughly 350,000 years. Even 99.9% of light speed leaves an onboard journey near 112,000 years. Greater time dilation requires speeds pressed increasingly close to the limit, and each improvement demands sharply more energy. At 90% of light speed, 1 kilogram of moving mass carries roughly 1.2 times 10 to the 17th joules of kinetic energy. That is comparable to the explosive energy of nearly 30 million tons of TNT concentrated into the motion of a single kilogram. A modest spacecraft would contain many thousands of kilograms. Its propulsion system would also need fuel or another energy source, along with a method for converting that energy into directed motion. The vessel must eventually slow down. Reaching cruising speed solves only half of the velocity problem. Arrival requires removing nearly all the kinetic energy added during departure. A craft unable to decelerate would cross Andromeda's outer regions at enormous speed and continue into the darkness beyond. Intergalactic space contains little matter, though extreme velocity makes even sparse particles dangerous. At 90% of light speed, a hydrogen nucleus striking the hull carries the energy of a high-energy particle produced in a powerful accelerator. A small grain of dust could release an impact comparable to a large conventional explosion. Shielding would need to absorb radiation and particle collisions for hundreds of thousands of years. The forward surface might require thick sacrificial layers, magnetic deflection systems, or a constantly renewed cloud of protective material traveling ahead of the vessel. Mechanical reliability becomes a deeper problem than ordinary maintenance. Components would fail through radiation damage, microscopic impacts, chemical changes, and simple wear. Every essential system would need the ability to diagnose faults, manufacture replacement parts, and recover from failures without assistance from its origin. A crewed mission would also need a closed ecosystem capable of recycling air, water, nutrients, and waste across geological timescales. Human populations would require enough genetic diversity to avoid severe inherited problems, along with stable methods of reproduction and education. Generation ships imagine many human lifetimes passing aboard the same moving habitat. Embryo missions would send stored genetic material to be raised by automated systems after arrival. Autonomous probes might avoid biological needs while carrying machines capable of repairing and reproducing themselves. More distant proposals imagine post-biological travelers, artificial minds or heavily modified descendants, able to tolerate durations that ordinary human bodies cannot. Every option introduces assumptions far beyond demonstrated engineering. After hundreds of thousands of onboard years, the arriving travelers could belong to a species, culture, or machine lineage, with little connection to the civilization that began the mission. Earth would have passed through millions of years of geological and biological change. The crossing would become an independent history, moving through space rather than a voyage connecting two living societies. A message requires no habitat, food supply, or deceleration system. It can travel at light speed from the moment it is transmitted. The same distance still controls how long the message must remain unheard. A radio message aimed at Andromeda would begin crossing the gap at the fastest speed nature allows. The signal would still need about 2.5 million years to arrive. Any civilization receiving it would hear a transmission sent when early members of the human family were living in Africa. Modern humans, agriculture, written language, and every present-day nation would all appear long after the message had left Earth. An immediate reply would require another 2.5 million years to return. The complete exchange would last roughly 5 million years. During that span, populations could evolve into new species. Languages could disappear without descendants. Continents would continue moving by hundreds of kilometers, while climates and ecosystems changed repeatedly. A conversation requires both sides to survive long enough to receive and understand each message. Across intergalactic distances, even perfect communication becomes a sequence of archaeological discoveries. The Virgo cluster makes the delay much greater. Its central region lies roughly 54 million light-years away. A signal transmitted toward one of its galaxies would arrive after about 54 million years. A reply sent immediately would reach Earth roughly 108 million years after the original transmission. 108 million years ago, Earth was in the Cretaceous period. Flowering plants were spreading across the continents, and large dinosaurs still occupied many terrestrial environments. A transmitter built during that era could only now be receiving its answer. The signal would also face practical engineering limits during its journey. Radio energy spreads as it travels. An undirected transmission expands outward in every direction, covering the surface of an ever larger sphere. According to the inverse square law, doubling the distance reduces the received intensity to 1/4. Across millions of light-years, an ordinary broadcast would fade far below the natural radio noise of space. A directed beam would preserve far more energy by concentrating the transmission toward a narrow target. Even a tightly focused beam gradually spreads because of diffraction. Diffraction is the natural widening of a wave after it passes through a finite opening such as a transmitting dish. A larger antenna and a shorter wavelength can produce a narrower beam. Over intergalactic distances, the illuminated region could still grow wide enough to cover thousands of star systems. The transmitter must also aim at the destination's future position. Galaxies move through space. Stars orbit within them, and any inhabited planet follows its star around the galactic center. A message aimed toward where a target appears today would be directed toward its position millions of years ago. Astronomers would need to estimate the target's proper motion, meaning its movement across the sky, then predict where it would be when the signal finally arrived. Small errors would grow across the crossing. At the receiving end, a civilization would need a large collecting area and instruments capable of separating an artificial pattern from natural radio sources. Pulsars produce regular pulses. Magnetars release sudden bursts. Active galactic centers can fill wide frequency bands with powerful radiation. A deliberate message would require recognizable structure, enough repeated information for error correction, and a receiver watching the correct part of the sky at the correct time. Expansion adds another effect over sufficiently large distances. As a radio signal crosses expanding space, its wavelength is stretched. The received frequency becomes lower than the transmitted frequency, and the arrival rate of its information is slowed. For relatively nearby systems such as Andromeda, gravitational binding keeps this cosmological redshift small. Signals sent toward remote, unbound galaxies would experience greater stretching during their journeys. Redshift weakens and changes the transmission without automatically destroying it. A sufficiently powerful receiver could account for the shift if the signal remained strong enough to detect. The greater obstacle comes from timing. Two technological civilizations might exist in separate galaxies and remain completely unaware of each other because their active periods never overlap in a useful way. One society could disappear 1,000,000 years before the other develops radio astronomy, while its final transmissions continue traveling through space. A receiver might detect a message from a civilization already extinct. Any response would begin another journey toward a world that had changed beyond recognition. Intergalactic communication, therefore, cannot create a shared present. It connects one distant era with another. Beyond the local group, accelerating expansion adds permanent causal limits to these already overwhelming delays. The galaxies remaining inside our gravitational region form the practical boundary of any future connection, while the wider cosmic web continues receding toward eventual darkness. The future of the local group has often been described as a collision between the Milky Way and Andromeda. For many years, simulations suggested that the two spiral galaxies would meet in roughly 4 or 5 billion years. Their stars would pass through one another with very few direct collisions, while gravity disturbed both disks and threw stars into new orbits. Repeated encounters would eventually produce one larger galaxy. That outcome now appears less certain. A study published in 2025, led by astronomer Til Sawala, used updated measurements from the Gaia spacecraft and the Hubble Space Telescope. These observations improved estimates of how Andromeda is moving sideways across the sky, a difficult measurement because the galaxy lies about 2.5 million light-years away. The researchers also included the gravitational influence of the Triangulum galaxy and the Large Magellanic Cloud. Triangulum can pull Andromeda in a direction that increases the chance of a future encounter with the Milky Way. The Large Magellanic Cloud affects the motion of our own galaxy and can shift the predicted path in another direction. When the full range of uncertain masses and motions was included, the simulations produced close to an even chance of a Milky Way-Andromeda merger within the next 10 billion years. Some simulated futures ended in a direct collision. Others produced a distant passage followed by a much longer orbit. A substantial portion avoided a merger during the full period studied. The uncertainty changes the details of the local group's future without changing its larger position in the universe. The Milky Way, Andromeda, Triangulum, and their many dwarf galaxies remain gravitationally associated. Their local motions are controlled mainly by their combined mass. Accelerated cosmic expansion will continue, increasing the distance to galaxy groups beyond this bound region. The local group will become increasingly isolated. During the coming tens of billions of years, galaxies outside our gravitational neighborhood will recede to greater distances. The light they emit will be stretched toward longer wavelengths by the expansion of space. Visible light will shift into infrared wavelengths. Infrared radiation will move into microwaves and radio waves. Each arriving photon will carry less energy, while the apparent passage of events inside the distant galaxy becomes increasingly slow. The galaxy itself will fade. Under standard projections in which dark energy continues behaving like a cosmological constant, most galaxies beyond the local group will eventually become effectively undetectable. After roughly 100 billion years or more, future observers may see little evidence of the rich galaxy population visible from Earth today. The Virgo cluster, currently observed about 54 million light-years away, will disappear from practical observation. More distant clusters will fade earlier from useful view, their last detectable light stretched across increasingly long wavelengths. The cosmic microwave background will also continue changing. Its present temperature is about 2.725 Kelvin. As the universe expands, its wavelength stretches and its temperature falls. Far future detectors would need to search at extremely long wavelengths while competing with radiation produced inside their own galaxy. Eventually, the ancient background may become effectively impossible to observe. In 2007, physicists Lawrence Krauss and Robert Scherer explored this possibility in work sometimes described as the end of cosmology. They considered what astronomers living in a very old universe might conclude from the evidence available around them. Those observers could inhabit a merged or rearranged local group galaxy surrounded by apparent emptiness. They might see no external galaxies and detect no cosmic microwave background. Without distant redshifts, they would have little direct evidence that space is expanding. Their visible universe could appear static and isolated. The hot early universe would still belong to the true history of their cosmos. Accelerated expansion would have removed many of the observations needed to discover it. The deep field image from the beginning of our journey now carries a different meaning. Its thousands of galaxies appear crowded because immense distances and many eras have been compressed into one flat frame. That view is also temporary on cosmic timescales. Humanity exists during a period when ancient light from remote galaxies still crosses the expanding gulf and reaches our telescopes. Those photons began their journeys long before Earth contained observers capable of receiving them. They passed through galactic halos, thin plasma, dark matter filaments, and growing regions of space. Their arrival allowed astronomers to measure distances, map the cosmic web, and reconstruct events from the universe's earliest visible history. Physical travel remains confined by speed and energy. Communication across the gulf cannot create a shared present. Cosmic horizons exclude most visible galaxies from any future contact. Knowledge has crossed where travelers cannot. The distance between galaxies separates locations, while light travel time separates eras. Expansion enlarges that separation, and the far future may remove much of the evidence that the wider universe was ever visible. For now, the sky remains open. Across its darkness, ancient light continues arriving from islands of stars that humanity may never touch, carrying enough information for one small civilization inside the Milky Way to understand the enormous universe beyond it.